Hello everybody, welcome back to another video. Today we're going to be solving a very fun calculus problem right here. So as you can see, we have the integral of 1 over 1 plus x squared dx. That's our integral, that's our problem. But the question in hand is, how can we solve this without arctan? So let me remove this right here. Traditionally, in school, in a class like AP Calculus BC or whatever appropriate calculus class you take, you will learn that the solution to this is just one of the trig integrals, arctan of x plus c. So this is what you traditionally learn, and it's a pattern you have to recognize. So if you have the integral of a du over 1 plus u squared, like that, you really learn that this is just arctan of u over a. So through these, you can solve all of these integrals, and there's this pattern you memorize, and it's really helpful when you're solving this. But the question is, how can we solve this without using arctan? So, ladies and gentlemen, that is the question for today. Let's get right into it. Now, when you're approaching this problem, one of the first things you might think of is, hey, look, can we try U-substitution? That's what a really early calculus student would begin to think. So let's see what happens if we do that. If we have, we have u is equal to the denominator, usually the most complicated part, 1 plus x squared, and then we take du. du is equal to 2x dx. Now, we can only replace this for u if we do have an appropriate du somewhere. But does it look like we have a 2x dx somewhere? We have our dx right here, and the constant is not an issue because we can just do 2 and 1/2, and it's equivalent, except we don't have an x in the numerator that we can use this with. So it doesn't look like U-substitution works. Now, a very common calculus mistake in really early learners is that they do continue to use substitution, and it doesn't quite work out. So they do integral of 1 over u, and they try to put the du. Now, they have to put because it's 2x dx, they put the x up here, they do 1/2, and they think that, hey, this is fine and we can solve this. But remember, our variable of integration is now du, and we have an x here, so this doesn't quite work the same. That's not how U-substitution works. Now, let's see what other options we have. So let's see here. We tried U-substitution, that can't work. We can't use arctan, so do we have any other solutions? Well, some of you might try to do this. If we have 1 plus x squared minus x squared, this is technically equivalent. It is equivalent to this because this is valid algebra. And then what people do is this is equal to integral of 1 plus x squared over 1 plus x squared minus x squared over 1 plus x squared dx, like that. And then this becomes 1, and then you have this term left. But as you can soon see is that the 1 is fine right here. But how can you solve x squared over 1 plus x squared? That this is a quite difficult integral because U-substitution doesn't work. You don't quite have many options here left. So let's try a different approach. Now, the key to solving this problem is, imagine if instead of 1 plus x squared, it said 1 over 1 minus x squared dx. Okay, remember, we can't use any fancy tricks or all, but let's say we factored the denominator. So we have 1 over 1 plus x, 1 minus x, because it's difference of squares. So through this method, you can see that we have partial fractions. And if you don't know what that is, you're about to find out. So using the same logic, can we factor the denominator of 1 plus x squared into some difference of squares or something? It turns out we can. So let's rewrite this integral as 1 over x, I'll put parentheses, squared, minus something squared. So x squared minus something squared is equal to x squared plus 1. We have to find n squared. So if we subtract x squared from both sides, we get this. We have n squared is now equal to -1 by shifting this on the other side and appropriately valid algebra. We get n is equal to I. We're not going to care about plus or minus right now. We just care about I, and you'll see why. So we get n is equal to I, so it turns out we can write this as a form of difference of squares. So this is equivalent, it turns out. the integral of 1 over 1 plus x squared dx is equal to the integral of 1 over x squared minus I squared, because x squared and I squared, square root being the, I being the definition of the square root of -1, I squared will be -1 minus -1, you get x squared plus 1. Voila. So you can use difference of squares here. Now the reason we didn't care about plus or minus is because when you factor this out into the difference of squares like this, if this is a minus I instead of a plus I, then this is just effectively swapping this like this. So it doesn't even matter. And because multiplication is commutative, it doesn't matter at all. So now with this in mind, this integral becomes really easily. So we have 1 over integral x squared minus I squared. Let's factor this out. X minus I, x plus I dx. Now we can just use partial fractions. So if we have something like this, let's say we have 1 over x minus a times x minus b, like that. It turns out we can write this into an addition or sum of two fractions in this form. A over x minus a plus b over x minus b, and that's capital B, so it's different. But we just have to solve for a and b. It's that simple. So we can divide this up and everything will work out. You're about to see what I mean by that. So we can take this entire fraction. We have 1 over x minus I times x plus I. This is going to be equal to something, some number, some constant over x minus I, that first factor right here, plus b over the other factor, x plus I. Now, let's say we take this entire equation, because we're trying to solve for a and b, we multiply this by x minus I times x plus I. Valid algebra. This is simple algebra. Cancel, cancel. And on this side, what's going to happen is we're going to get 1 is equal to x plus I times a plus x minus I times b. Now, this equation holds true for all of x. We're just trying to find a and b, and it turns out there are many ways of doing this, but I'll use my favorite way. We can just let x equal something, and it'll cancel out very nicely. So let's say let x equal to I. What happens? That means 1 is equal to 2i times a plus I minus I, times b. I minus I is 0, and this b term gets eliminated. Then we have a is equal to 1 over 2i. It's that simple. Now you can do this again. I'll do it for the purpose of the video. Now we have let x equal negative I. What happens? We have 1 is equal to negative I plus I times a plus negative I, or negative 2i, like this, times b, if you just plug it into this equation. Now, negative I plus I is 0. This all cancels because we don't care about a right now. Negative 2i times b is equal to 1. b is equal to negative 1 over 2i. So now we have our constant values for a and b, meaning we can rewrite 1 over x minus I times x plus I into the sum of two fractions that we can easily integrate. Now let's do that. So I'm going to draw an arrow, and I'm going to use a better color like this, green. So this integral is going to equal 1, I'll write it like this. So we have the integral of 1 over x minus I, x plus I, dx is equal to the integral of a over this factor. So we have 1 over 2i, 2i, all over the factor right here, x minus I, plus, or I'll pull out this minus because b is negative, minus 1 over 2i, x plus I dx, just like that. Now there you will see some pretty cool algebra right here. We can just pull out that 1 over 2i because it's a constant. Then we'll get that this is equal to 1 over 2i times the integral of 1 over x minus I minus 1 over x plus I. Ladies and gentlemen, we are almost there. We only have a few steps left, and we'll have our answer. So this is a constant, of course, I being the imaginary unit. So this is equal to 1 over 2i times the integral of this. But now let's just integrate this. We have everything necessary to integrate. If you have the integral of 1 over x minus a, where a is a number, dx, this is just equal to ln of absolute value of x minus a, plus c, of course. And why is that? Because if you let u equal x minus a, du is just dx. So you can replace all this with u, and then you can use the ln rule to get ln of absolute value of u. And then you substitute u back in, and then that's your answer. Now, if you want a video on the basics of calculus and why this is true, I can do that, but let me know in the comments down below. So using this property, we can, of course, say right here, this is going to be equal to, let's integrate this part. So we have ln of absolute value of x minus I, and then we have to integrate that part, minus ln of absolute value of x plus I, just like that, plus c, because now we're done with the integrals. So, ladies and gentlemen, you'll see that we came from this integral right here, and we've solved it effectively. But are we done, or are we missing something right here? Now, let me write this a little more cleanly. 1 over 2I, right here. ln of absolute value of x minus I. Now, what you learned in calculus class, that when you're integrating something over like 1 over x minus a, this is going to be ln of absolute value of that, of the thing in the denominator like that, of x minus a. Now, the issue with this is that when you take the absolute value of something imaginary, you get the magnitude of that imaginary term. So, if you take the complex plane right here, let me draw it out like this. You have, we'll do this as real, and this is imaginary. So let's say this is I right here. This is essentially like 1, but we just say it's I in the imaginary plane. This is 1, 2. The absolute value of I would be that magnitude of I, which is, you've probably seen that symbol before if you've done physics. It's the magnitude of I, and the magnitude means the distance from the origin. So thus, if we said the magnitude of I, this would be 1. But that's not what we're looking for. We do literally want to take the ln of that imaginary number. So we shouldn't be doing absolute value in that sense because we're not looking for the magnitude. The reason that we do absolute value is because we're not looking for ln of a negative number typically, but I'll talk to you about that in just a second. But in this case, we are looking for that because we're working with complex numbers. So that's an exception to the ln rule. I can explain that more, but for the purpose of the video, we'll just continue going forward. But yeah, in summary, we don't use the absolute value because it indicates magnitude more than the actual non-negativeness, which it's typically used for. So we can write this as ln of x minus I minus ln of x plus I plus c, of course. Now, when you graph this into Desmos, it turns out that you will have the correct answer, and if you use the complex mode, of course, otherwise you can't graph it. So if you want to do it, go for it. But you'll notice that if you rewrite this using ln rule, one of the properties of logarithms, you will see something. So if you don't know already, ln of a minus ln of b is equal to ln of a over b. This is just a property of logarithms. It's just how they work. I can do a video explaining that, but that's just basic algebra too. So assuming all of you know that, we can say that this is just going to be, we're going to divide. So ln of x minus I over x plus I plus c, just like that. And then we get ln of 1 over 2i, I'll remove the parentheses, x minus I, x plus I, plus c. That's our answer. Now, when you graph this out into Desmos, you'll notice that you do get a little jump in the graph. It becomes like piecewise almost. So the graph of arc tan x looks like that, but Desmos graphs it like this, and then it jumps down here and does something funny. This is just Desmos being weird. This is an issue with Desmos. Remember, no graphing editor is actually perfect. It's just a Desmos issue, so there's nothing to worry about. It is indeed equal to our function. It is exactly equal to, strictly, to arc tan of x. So yeah, there's nothing to worry about here. If you're thinking, hey, this is false information, no, it's just Desmos being weird. And if you want to really analyze this, or write it in an even cooler way, I'll put it in red. ln of the 2ith root of x minus I over x plus I. But that's just messing with the logarithm and its properties, plus c. And that's the answer to our integral. And that means, because we do know from our calculus class that this is equal to arc tan x plus c, we can say that this solution right here is equal to arc tan x plus c. And this is the closed form solution. We did not do some expansion or any of that. But yeah, I hope you guys enjoyed this video. If you have any questions or if I made any mistake anywhere, feel free to let me know. Once again, thank you guys. If you have any video ideas, leave them in the comments down below. Thank you guys. See ya.